In this lecture, we talk about character of a representation. So let us start by introducing the trace of the matrix. So recall, if you're given n by n matrix, the trace of the matrix is nothing but the sum of the diagonal entries. So you sum up the diagonal entries. So one important property of the trace is that trace of product of two matrices is trace of PA. So matrices are not commutative, but their traces are commutative. So obviously AB in general is not equal to BA, but traces are. So this is important because now you can have an invertible matrix P and you can have trace of P inverse MP is equal to, now you can commute these two, this P can go here, these two will cancel out, giving you identity matrix is trace of M. So similar matrices, so these are, so M and P are similar matrices because they're related like this. So for similar matrices, you have the same trace. So in case you have a linear map phi going from V to V and say V has basis B, then trace of phi is independent of basis because you can relate two bases via some similar matrices. And then you apply the same procedure for two different bases. So now let us come to the definition of representation of G and the associated character. So let V be the representation of G and say the character of V, which we denote by chi. We sometimes write subscript V. This is a function giving from group G to complex numbers. Instead of complex numbers, you could have any other thing K here. So basically you're taking an element G and mapping it to trace of row of G. So more formally, we will write chi of G as trace of row of G. So sometimes we write this vector space V and sometimes we skip it. So we will most possibly not write this vector space V, and it will be clear from the context which vector space we are working on. So let us immediately give an example. So consider this dihedral group D2n where n is odd. So it is given like this. There are two generators A and X, and so A is the rotation of the n-gon and X is the reflection. So we can talk about its representation in R2. So the vector space is R2. So A is mapped like this. So this is just the rotation. If you do A to the M, it is mapped like this. So basically the same matrix is coming here. You're putting M extra. So X is just a reflection, and then AMX is just reflection around any rotated line. So now you can talk about characters of these matrices. So character of this element here, so we are talking about every G, so character of now X you can see is 0, sum of these two elements. Similarly, character of this is also 0 because it's sum of cosine this element and this element, because you're talking about the sum of the diagonal elements. So this is positive cosine, negative cosine will be 0. Now character of this is obviously sum of these two elements, which is going to be 2 cosine 2 pi k m by n. So that is similarly here. So you can talk about this, which is going to be 2 cosine 2 pi k over n, sum of these two elements. So now let us discuss some properties. So consider a complex representation. So we are working over complex numbers. This representation rho V of G, we'll take G as a finite group with this character chi. So then chi of E, where E is the identity element of G, is just dimension of E. So this is just clear. Chi of E is nothing but the corresponding matrix corresponding to E, which is the identity matrix, and the trace of the identity matrix is just the dimension of E because you're adding all the bonds along the diagonal which represent the dimension. So for a 3 by 3 matrix, you will have zeros in the top and bottom, and you add them up, you get 3. So second is this chi of G is this chi of H, G, H inverse for all G, H and G. So this conjugation doesn't change the character, and this basically pops out from this formula here, which we have talked about before. So let us see this. So this is rho of G is the matrix associated with G. So this is equal to rho of H, G, H inverse, which you write it like this, but now this is a matrix, this is a matrix, these are similar matrices, and therefore they will have the same trace. So chi is trace of rho of G, which is also, this is also trace of HG H inverse, this here. So this -1 actually comes out like this to just show you that rho of G and these two matrices are similar or conjugate to each other, and therefore they have the same trace. Essentially the same argument here comes right here. So yeah, so one should not get confused by inverse inside, it comes out. So for number 3, this chi of G inverse is just the conjugate here. Obviously conjugate we are talking about in complex numbers because chi of G is landing in a complex number. So we are thinking of something like this. So you have conjugate on this side for inverse. So this requires some facts from linear algebra. So again, you know, for eigenvalues for a matrix A, you write it like this. So this psi I is the eigenvector and this lambda I is the eigenvalue. So this is the eigenvector and this is the eigenvalue. So then you can write this eigenvalue matrix. So you can consider all these eigenvalues and the corresponding eigenvectors. Then you can have two matrices. One matrix is this big capital lambda, and this is a diagonal matrix. So it has zeros everywhere except on the diagonal it has the eigenvalues. And then you have this matrix psi which has all your eigenvectors. Then we can write this matrix A as this psi lambda psi inverse. So obviously we are writing like this because you can see these are similar matrices. So if a rho of G has eigenvalues this, then since similar matrices will have same character, you can talk about chi as being the sum of the eigenvalues. So essentially again we are using this property of similar matrices but now applied to this thing here. So instead of A we are considering this rho of G. So if the order of group is n, then G of n is E, or rho G of n is this identity matrix. So if you are going to use this identity matrix and put it right here, then your lambda I to the n has to be 1. So again this is just following because this rho G of n is identity matrix, this will also become rho G of n, and then you can again use this thing here. So lambda n is 1, which means that these eigenvalues themselves are roots of unity. So this lambda I is a root of unity. So if lambda I is a root of unity, then lambda I inverse is lambda I conjugate. So this is a fact from complex analysis for roots of unity. And another fact again you can draw from linear algebra is that rho of G inverse, the eigenvalues are lambda I inverse. So that you can again see here, you can take inverse of both sides, you will get lambda inverse in between. So therefore this character of G inverse is actually corresponding eigenvalues are lambda I inverse. So you have lambda I inverse values, which is same as summing up over lambda I bar, because of this equality comes right here. This is because the eigenvalues are lambda I inverse here, and this is precisely what is conjugate of chi of G, because chi of G is nothing but this, and taking conjugate of this becomes this. So number 4th, so this is again a linear algebra answer. So if rho prime v prime is another representation of G with character chi prime, then the character of v direct sum with v prime is chi plus chi prime. Now this is simply because this direct sum will give you a diagonal matrix. So say it gives you some diagonal matrix like this, zeros here, zeros here. So for chi you are adding the diagonal elements here, for chi prime you are adding the diagonal elements here. So for this entire matrix you are adding all the diagonal elements, which becomes this. Now this tensor v prime is just the product of characters, but this tensor, again this is just computational. If you expand it out, you can see this is nothing but Kronecker product. So you can Wikipedia it, and on Wikipedia you will get nice examples of finding Kronecker product of two matrices, and then you can see if you see the diagonal elements, that is just going to be the product of the characters. So this follows from the block diagonal, so this follows from the block diagonal, and this second part product follows from the Kronecker product of the matrices.